This is Lab 3 for Physics 2211 Black Hole Lab. In this video, we will be using fundamental physics principles to find unknowns given certain information. In Part 1, the goal is to deduce the mass of a black hole being orbited by a star, and in Part 2, the goal is to come as close to that black hole as possible, without being sucked in by finding an acceptable initial velocity. Principles governing this lab are the universal law of gravitation and Newton's second law. Newton's second law, also known as the momentum principle, can be summarized in the rearrangeable equation delta P equals F net times delta T. This principle extends to circular motion, where F net can be broken into its components F parallel and F perpendicular, where their sum is F net. F parallel describes the magnitude of the change in momentum, while F perpendicular describes the change in the direction of the momentum. The second principle we will utilize is the universal law of gravitation. This principle relates the mass of two objects and their distance from one another to find the force of gravity between them. In this lab, we assume that gravity is the only force present in the motion of the objects, so our F net will be equal to Fg. Because universal gravitation is a non-constant force, when we use the position and velocity update formulas utilizing F net, the average velocity will be the final velocity from the previous time step of each iteration of our calculation. In Part 1 of this lab, the system is a star orbiting a black hole, and the surroundings is the black hole. The initial conditions for the system are a star with mass 2 times 10 to the 30th kilograms, starting at time 0. The data points generated by my email address have a delta T of 1 day on Earth, or 86,400 seconds. The universal gravitational constant is 6.7 times 10 to the negative 11th. The code and glow script for the first half of this lab uses two while loops. The first extracts velocity data from the position and time data, generating a list of x and y velocity values by dividing the change in position by change in time for each time step. The second while loop uses these generated velocity values to compute the change in momentum, first by finding the change in velocity, then a change in momentum by multiplying the velocity values by mass and finding their difference. Then dp over dt, or the rate of change for the momentum, is computed by this change in momentum divided by the change in time. Calculation of mass of the black hole, I first related dp dt to F net based on the momentum principle. I then calculated the parallel component of the change in momentum by taking the magnitude of the final momentum and subtracting the magnitude of the initial momentum from it, dividing the result by delta t. I then multiplied this result by the unit vector and related its value to the parallel component of F net. To find the perpendicular component of F net, I subtracted F parallel from the total F net. To solve for the mass of the black hole, I rearranged the universal gravitation law formula to isolate the mass, and assuming that gravity is equal to F net in this system, I plugged in r squared, the star's position minus the origin, noted by the location of the black hole, F net, the star's mass, and the universal gravitational constant, g. I then ran the program and averaged all of the mass values in Microsoft Excel to produce a final answer. From the simulation, we see that the magnitude of F net is growing, showing the necessity of averaging the mass instead of taking it as it is, since it's proportional to this changing F net. The average mass of the black hole in this lab was 1.138 times 10 to the 34th kilograms. One potential source of error in this part is inaccuracy in the mass due to not having enough data points, and in the future I could run the program for longer. The what does it mean question of this lab asks what the difference is between the components of net force and components of dp dt. Because of Newton's second law, there is no difference between them. For part 2 of this lab, the system is a ship orbiting a planet that is orbiting a black hole. The surroundings are the planet and the black hole. The mass of the planet is 9 times 10 to the 28th kilograms, the mass of the ship is 7 times 10 to the 10th kilograms, and the mass of the black hole, determined by part 1, is 1.14 times 10 to the 34th kilograms. The planet's speed was found using a rearrangement of the universal law of gravitation, and the program runs with a t maximum of 2 hours to better visualize the planet's orbit. To simulate the movement of the ship and the planet, I used a while loop to find the total force acting on the ship and the planet. First, the total force acting on the ship was calculated using the universal law of gravitation's formula in relation to the black hole and ship respectively, and the same process was repeated for the total force acting on the ship. To actually find the initial velocity of the ship that disallows it to crash, I used the method of trial and error. I found a rough starting point, knowing that the x direction would be negative as it is being pulled inward due to gravity, and the y direction would be positive to avoid hitting the black hole straight on. I deduced a rough magnitude by guessing a rough escape velocity from the planet and tweaked the numbers from there. From my trial and error calculations, the most ideal initial velocity for the ship not to crash is shown on screen. One potential source of error in this part is inaccuracy in the initial velocity due to the trial and error process. Also, my results in this part can be skewed if the calculated mass in part 1 was affected by error. If instead I wanted the ship to orbit the black hole, the initial velocity would have to be the one shown on screen.